Today I'll explain greedy algorithms. A greedy algorithm always makes the choice that looks best at the moment. It makes a locally optimal choice in the hope that this choice will lead to a globally optimal solution. It makes the choice before the solved problems are solved. So I'll explain an example problem. It's an activity selection problem. It is to select a maximum size subset of mutually compatible activities. For example, there are n classes and only one lecture room. And we have to select the maximum number of classes to be held at the classroom. It is this. We are given a set of activities, and the set is denoted by big S. Each AI is an activity, and each activity AI has its start time Si and finish time Fi. Start time is earlier than the finish time. Now look at this. We have 5 activities. A1 starts at 1 and finishes at 4. A2 starts at 3 and finishes at 5. And we assume that activity AI takes place during this period of time. That is, start time is included and the finish time is excluded. So, okay, and activities AI and AJ are compatible if the intervals Si, Fi, and Sj, Fj do not overlap. Look at this example. A1 and A4 don't overlap and they are compatible. How about A1 and A2? Are they compatible? 김기호. 김기호? 송민철. 김민석. Are A1 and A2 compatible? They aren't compatible. And how about A2 and A4? Kim Jong-jun. A2 and A4, are they compatible?
No.
Why not? They are compatible. So the finish time can overlap to the other's start time. So it's fine. Yes? Okay, so look at this. We have 11 activities. And think about a set of A3, A9, and A11. Are they mutually compatible? Yes, they are mutually compatible. There is no overlap between any pair of activities. But it's not a larger set. We can find a larger set. Can you find one? 이현진. Can you find a larger set? A3, A7. Can you find the largest set, including that? 윤재철. A2, A4, A8, A11. Yes, it's a larger set. The larger sets are not unique. A1, A4, A8, A11 is another larger set. And this is what you said. A2, A4, A9, A11. So, from now on, I'll explain how to find the largest set. And we only consider the numbers in this set. We don't consider the lengths of the intervals. First, we sort all activities according to their finishing times. Let me explain this. Now the activities are sorted according to their finishing times and in increasing order. And we select the earliest finishing activity one by one. Look at this. First, A1 has the earliest finishing time, it is included. And then check A2. Is A2 overlapping or non-overlapping? It's overlapping, so it is not selected. How about A3? Overlapping. A4? Non-overlapping, so it is selected. A5, A6, A7, and A8. Good. A9, A10, A11. 11 is included. So one of the largest sets is A1, A4, A8, A11. Then it's time to prove that this is right. Why? Why this algorithm right? Think it over for a couple of minutes. This algorithm is selecting the early we can select, there are multiple choices, but when we select an activity, we select with the earliest finishing time. Then we can select a maximum number of activities, non-overlapping activities. So how can we justify the algorithm? Assume that A1 isn't selected. Then another activity was selected. Then its finishing time is later than A1. So the empty slots are reduced. So that's why the earliest finishing time activity is selected. Okay? That's the main idea. So let me compare the greedy choice and dynamic programming. In this case, we make the choice before the problems are solved. That is, we select A1 without without determining which activities are selected in the other sub-problem. But in the case of the dynamic programming, we make a choice after all the sub-problems are solved. So this is important. We make decision before sub-problems are solved. Okay, let's compare the greedy method and dynamic programming method. There are two kinds of knapsack problems, O1 knapsack and fractional knapsack. Let me explain the O1 knapsack first. The main character of this story is a thief. A thief is trying to rob a store, and in the store there are n different kinds of items. And each item has different worth and different weight. So the ith item is worth VI dollars and weighs WI pounds. And he can carry at most big W pounds in his knapsack. And N, VI, WI, and big W are integers. Then which items should he take? In this case, you cannot cut items. Assume that it's a cell phone. You cannot cut it. You can cut it, but it is worthless when you cut it or break it. But if it is a gold bar, then you can cut it. So then the problem is reduced to a fractional knapsack. In this case, the thief can take fractions of items. This problem is simpler to solve. So think about this.
Professor, you mean that he can cut the item?
Cut an item and take any fraction of it. Yes. We can use the greedy strategy. We first compute the value per pound. That is VI over WI for each item. Take as much as possible of the item with the greatest value per pound. Okay? And look at this. In this case, we have 3 items. First item, second item, and third item. And it weighs 10 pounds and worth $60. 20 pounds, $100. 30 pounds, and $120. Then, what is its value per pound? 나무점 for item 1. Value per pound. 박헌호. 전호근. Six, yes. 60 over 10 is 6. 조형석, what is the value per pound for item 2? $5, yes. 100 divided by 20, it's 5. And it's 4. So this is very effective and less effective and ineffective. So the thief put item 1 first and then item 2 and only 2/3 of item 3. This is optimal. So he can get $240 worth of items. But this algorithm doesn't work when it comes to the O1 knapsack problem. Let's see. Let's fill the knapsack with the same algorithm. We first put item 1, then put item 2, and the remaining capacity doesn't fit for item 3. So he can get only $160. But there are 2 other choices. In this case, it's item 2 and item 3, and in this case, it's item 1 and item 3. Then it is 220 and it's 180. Okay? So the greedy strategy doesn't work on this problem. We have to use a dynamic programming approach, and it's your homework. And then I'll explain Huffman codes. Huffman codes is a widely used technique for compressing data. First, let's consider representing 100,000 characters from this alphabet. This alphabet has only 6 characters, A, B, C, D, E, F. And what is the normal representation? Because we have 6 characters, we need at least 3 bits to represent 1 character. Okay? 2 bits are not enough. We need at least 3 bits. Okay? So let's represent them with 3-bit fixed length code. A is by 3 zeros, and B by 001, C by 010, 011, 100, 101. Okay, this is a normal way to represent 6 characters. Then what is the total number of bits to represent all 100,000 characters? It is 전동엽. How many bits are required to represent all these characters? 18? 8? 9? 최윤주. Yes, 300,000 bits are required. 3 times 100,000 is 300,000. So we need these bits, but we can reduce them. Look at this. In this case, we don't use fixed length code word. We use variable length code words like this. A is represented by only 1 0. B and C are represented by 3 bits, including D. And E and F are represented by 4 bits. Then, let's count the number of total bits. The secret is here. The secret is all characters doesn't appear evenly. Some characters appear frequently and other characters appear infrequently. So A appears 45%, B 13, C 12, D 16, E and F are 9 and 5%. So we assign shorter code words for frequent characters. So A is the most frequent. It was assigned a code word of length 1. And these 3 characters are assigned 3-bit code words. And least frequent characters are assigned 4-bit code words. Then, let's calculate the number of bits. Then it is 224,000 bits. Okay? So we can reduce the number of bits if we use a variable length code. But if we use a variable length code, encoding and decoding is quite difficult. Encoding is quite simpler. So this is the code word we used in the previous page. Encoding A, B, C is just concatenate these 3 code words, 0, 101, and 100. So this is the encoding. But look at this. We have to decode this. Decoding is difficult because we cannot separate the code words easily. If we look at this carefully, you can do it. A, B, E. Okay, let's go reverse. If you concatenate these 4 code words, you can get this. But until now, decoding is hard. Let me explain how to decoding 10 minutes later. Before I explain that, sometimes decoding is ambiguous if we use an ambiguous code word. Look at this. Assume that A is by 0, B is by 0, 1, C is represented by 1. Then we have to decode 0, 0, 1. Then what is the decoded message? It's ambiguous. There are 2 decoded messages, AAC and AB. AAC is possible because A001 is AAC. And AB is also possible because 0 is A and 01 is B. So we have to create the code word very carefully. So the answer is we have to make a prefix code. That is, no code word is a prefix of some other code word. Look at this. This is the code word we used in this lecture, and this try shows that no code word is a prefix of another. Look at this try carefully and try to understand this try. Okay, can you explain the try? How can you create this try from this code word set? Haojun, can you explain how to create this try from this code word set?
Firstly, we will consider the first character, and if it's 0, it will be 8. And then we consider if it's 1, then it can be divided into 2 sets. If it's 0, so it will be this side, and it will be C or B. If it's 1, it can be EDF.
Yes. First, try edge is labeled by a bit, okay? And the right child, the edge to its right child is labeled by 0, and the edge to its left child is labeled by 1. And let's create this try using this code word. A is 0, so it go right, left, and it is this. And B, 1, 0, 1. This is the B's place. C, 1, 0, 0. D, 1, 1, 1. E, 1, 1, 0, 1. F, 1, 1, 0, 0. So in this way, you can create a try. Then now you can see that there is no code word is a prefix of another by looking at this try. How can you know that? Okay, assume that F and E are here. Then there is another character G. And the code word of G, assume that it is a prefix of F. Then what happens? Where? Where does it add it? No. If it is a prefix, it should appear among these 3 internal nodes. Do you know what is a prefix? prefix가 뭔지 알아요? 접두사. If this is a string, 0 is a prefix. And OO is another prefix. This is another prefix. And this is the longest prefix. So, if one code word is a prefix of another, it should appear in the path from root to another character. So, in this case, all code words are in the leaves. They are all in the leaves, not internal nodes. So it's prefix codes. It depends on the frequency. but there is only some of them are optimal. Finding one, to find it is the main topic of this lecture. Okay, then I'll explain that we can decode using the try. Zero zero 1 0 1 1 1 0 1. Okay, let's decode this bit string using this try. When you decode, at least this table is given to you. And then you create this try from this table. It is not difficult. You can generate a try like this. And then we can traverse the try using this given string from the root. Yes, the first bit is 0, so we go left. Then it's A, so A is decoded. Then we get back to the root again, and then start traversing. And it is 0, another A. And then 1 0 1. It's B. Then go to the root again. And what is it? 1 1 0 1. It is E. Now we can decode the encoded bit string. And I will explain prefix codes in detail. This is the try we used. And this is the try for the 3-bit fixed length code. For A, 0 0 0. And for B, 001. For C, 0 1 0. And for D, 0 1 1. So this is the try for the 3-bit fixed length code. When there is an important difference between these two, and look at this, all characters are in the leaves. So this is also a prefix code. If one is a prefix of another, it should appear in an internal load, but there is no such case, so they are both prefix codes. But this is more efficient than this prefix code. Let me explain why. Okay, look at this tree, and this tree is a full binary tree. What is the definition of the full binary tree? 김기호, 송민철. What is the definition of a full binary tree? Except leaves. Leaves have no child, and internal nodes have 2 children. That is a full binary tree. But in this case, it's not a full binary tree. Why not? 김민석. Yes, this is not a, this node has only 1 child. So this tree is not a full binary tree. If a tree exactly a trie isn't full binary trie, then it is inefficient. There is something to optimize. What is it? 김정준. So in this case, the code word for E and F are 100 and 101 respectively, right? But it is quite long. We can reduce it. Can you see the point? This one is necessary to distinguish E and F from A, B, C, D. And this one, 0 and 1 are important to distinguish E and F. But this 0 has no role. It is redundant. Okay? So, if the code is optimal, it should be a full binary tree. Then how can we create a full binary tree? All full binary trees are not optimal. Only some of them are optimal. It is this algorithm to find an optimal full binary tree, a Huffman code. And this algorithm is very simple because it uses a greedy approach. So we have 6 characters and their frequencies. And then first we select 2 infrequent characters. 2 most infrequent characters. What are they? 김규동. What are they? 2 most infrequent characters. 김대건. What are the most infrequent characters? Okay, then the next, the second infrequent character, E, F and E, right. F and E are the 2 most infrequent characters. And then we create a subtree merging E and F like this. And assign a frequency to this internal node. They are 5 plus 9, 14. And one is 0 and one is 1. And their orders aren't important. In this case, F is 0, E is 1. But E can be 0 and F can be 1. They are symmetry. And then we do this repeatedly. Now we have 5 nodes. And then select two most infrequent vertices. What are they? 박진석. C and B, right. They are C and B. So we merge them and create a node with a frequency 25. 방재홍. What's next? DNA? No. We have 4. Yes, 14 and D. we create a node and its frequency is 30. 박영료, what's next? 25 and 30. Yes? This. And finally, we create a try like this. It's done. Very simple. Then, the code word for A is 0, and the code word for C is 100, for B is 101, in this way. So when we encode, we first calculate the frequency of each character. And then with that information, we create a try using this algorithm. Then we can create a code word table. Then we can do the conversion once we have a code word table. Right? Okay, I explained a Huffman code. And this algorithm is very simple, but its analysis, it's not easy. So I'll explain it next week. And my last comment is, please do the review when you come to this class, especially for the next class. So I'll talk about the correctness and the running time of this algorithm, but you have to remind you yourself of what I taught in this class. Okay? Okay? Yes? See you next week.